But I thank the organizers for letting me speak in today and for the invitation as well. But as it was mentioned, in the last year, we have been working quite a lot to trying to understand how to properly train the restricted Boltzmann machine. And in this sense, the talk from Guillaume was quite useful because you have already been introduced, especially on the interest of using a restricted Boltzmann machine for something. No? So well, the work I will be presenting, it was done most in collaboration with Aurélien Dessel and Cyril Furlerner. And the last part of the talk that I will speak about some work that is not just finished about bias sampling. It was done by a student that was visiting Madrid for several months, Nicolas Beru. Okay, so the generative approach is quite simple. We have data, we want to feed it to the machine, and we want that the machine later creates new data that looks very much like the original data. I will show examples of MNIS, which is writing digits. It can be faces of celebrities. We have some data of genome sequences, and also, well, briefly, I will mention protein sequences that are protein families, like it was introduced by Jerome, that are tied together by evolution. So this is, we have a step that is the training, we feed data, and a step that is generated, we create new data. Okay, there are many different ways of doing this task. I will mostly speak of the so-called energy-based models that contains the RBMs, but in the recent years, they are a lot more popular. The generative adversarial network that have been mentioned several times in this conference, the variational countercoder, and so on. Okay, the energy-based models are called like this because they are based on a function of an energy that we assign to the data. So this energy is going to depend on the observed data, but also of some variables that we are going to introduce, which are latent variables and certain parameters that we want to feed during the learning. Okay, so once we have this energy, we can assign an normalized probability to this energy. So the goal of the learning is to find the parameters so that the data set can be typical samples of this probability. Okay, this is normally done by maximizing the log likelihood. That is nothing but maximizing that the probability of finding the samples that we had in our data sets is maximized, and we do it by gradient accent. The problem of all this approach is that, of course, we don't know the normalization function of our probability. We don't know the partition function. So if we want to compute the log likelihood, we can only do it if we could exhaustively search all the configurations, which is impossible for an interesting data set. So we need to do Monte Carlo sampling. And all the difficulties come here. Okay, the energy-based models can be the restricted Boltzmann machine that I will mention, in which we just have one layer of latent variables. We could have several layers of latent variables, or we can even have complex deep networks with convolutional layers, but all of them work in the same way, assigning an energy to our system. Why do I want to study the restricted Boltzmann machine? Okay, the first thing is that they are essentially an easy model. I'm a statistical physicist, so I like the easy model. But it's a model that is complex enough to actually be able to fit any kind of data set. This has been proved. It will be overfit, but it can do it. And one of the nice things is that, as I said, if we have the model, we can obtain a normalized probability distribution function for the data, and we can try to analyze what the machine learns. So we have the possibility of doing some interpretability of the features extracted, which would be quite difficult if we had a more complex network. The problems of restricted Boltzmann machine, they are quite hard to train or to properly train. They behave in a weird way. Many times very uncontrolled. You don't know why. You have trained it, and it starts to generate weird things, very unbalanced things. Or it can be even that you have a good model, but when you try to generate new samples, it takes really, really long time to get something good. And also, one of the main drawbacks is that it doesn't include convolutional layers. So for certain data sets, it can be really a problem. Okay, the restricted Boltzmann machines, they were introduced a long ago, and they were very popular until, I don't know, 10 years ago. But they were decreasing in time, especially for a lot of time. They were used as units, pretend units for more deep network structures. But in the last years, they are a bit in decadence as generative models, and they have been clearly overpassed by GAN and variational intercoders alternatives. But on the other hand, from the statistical physics point of view, it has advanced our understanding of the problem. It has advanced a lot. Now we have a phase diagram for the RBMs. We know a lot about the learning dynamics, and we even have better algorithms, like based on the message passing algorithm. Okay, the restricted Boltzmann machine, as I said, they are formed by two layers. We have the visible layer, which corresponds to the data. We have images, it will be the pixels, and we have the hidden layer. Okay, for all my talk, well, the last part is not exactly the case, but we are considering that both variables, they just can get two kind of values. Like if they were spins up and down, but here we have 0 and 1. And we consider that they have an interaction function, which is quite simple. Visible units only interact with the hidden, and the same in the other way around. And later we can allow also fields interacted with each of these variables. Okay, the hidden units are the neurons, and they allow us to extract the features of the data, and they allow the interpretability. In fact, as was discussed by Tubiana, it's precisely this what is attracting a lot of attention from the biological, the computational biology contest, especially from the sequence contest, because if we are able to obtain this model, we can try to understand and to get some properties of the enormous quantity of data that we have that we don't understand. So just to repeat, all these models, they have two different periods. We have the training, in which we try to fit the parameters, and we have the generating sampling, in which once we have the quench parameters, we generate new samples that we are going to do it with Monte Carlo. Sorry. Okay, when I mean sampling, that's what I was saying. We want to do, okay, we can think that that the restricted Boltzmann machine is too simple, but for instance, I can show you. It does not. For this, it doesn't work, but I can show you that it was a gift, but that's not. Okay, anyway, it's not so important. The point is that we can start from, begin here. So the idea is, okay, we can start from just a random, we should start from a random picture, just gray, and if we start to sample our spins, our variables, at a certain moment we should reproduce images like the numbers or the faces. Okay, that's a bit sad because we could say, maybe later I managed to do it, we can see, for instance, with the faces that we create really, really good faces. I mean, they look quite real, and we are just speaking of a machine that doesn't have any kind of convolutional layers, and we just have variables that are 1 and 0. Okay, so we have our probability and normalized because we don't know the set. We have our data set, and we want to maximize the logarithm of the likelihood. Okay, we do it with the restricted with the model that I gave for the restricted Boltzmann machine, we get a gradient for the log likelihood, which is quite simple. It depends on the difference between an observable computed using just the data of the data set and the same expected value, but in the model of the RBM. Okay, before going more, just speaking about the interpretability, we can understand why this is interesting, because, for instance, if we start from the model the model I introduced for the restricted Boltzmann machine, we can see that if we compute the energy of a given visible configuration that is integrating out the hidden variables, we obtain an expression like this that we can develop in using Taylor expansion, and we can see that we would obtain an effective energy that contains all the interactions at all possible and odd possible degrees, which means that once we have a trained machine, we really have a very complex model for our data. So if we manage to train it well, this is really powerful. And other things, we understand a lot right now, at least the learning mechanism, and it is known, and it was studied years ago, that the learning procedure, the moment from we have a model that hasn't learned anything from the data to the point that we start to learn features, it occurs a transition from some kind of paramagnetic phase to a ferromagnetic phase, in which, if we study the weight matrix, the interaction between the hidden and the visible layer, we can see that a very strong eigenvector arises at a certain point during the learning. Here are the eigenvectors, so they start to grow. One can see that the transition corresponds to the point in which we have one of these directions that is very strong, and if we project our data along this direction, we're going to get a magnetization that passes from being 0 to being distinct from 0. So the machine is learning directions to split up the data. And this is very interesting because, okay, we have certain directions which are really, I mean, we have the different eigenvectors. And here, for instance, I show you for the projection along these directions of a data set of a protein family. That is a work that we have been doing with Alessandra Carbone in the Sorbonne University. And we can see that once we project along these directions, we start to get clusters a bit isolated. And later, if we color the proteins for which we know they have a different function, these are the different colors, we see that the machine is putting them together. So we are finding the directions that manage to split the proteins without any kind of previous knowledge, which is quite nice. Okay, so coming back to the computation of the gradient, okay, we had these two parts. This one is easy. We just compute it using our data. And we have this other part in which we have to compute expected values for the model of the RBM. And as I said, this is the difficult part because we don't know the partition function, but we use Monte Carlo. We could use other dynamics like Langevin or whatever, but okay, in our case, we do Monte Carlo and we do heat-bath dynamics. Okay, so the idea is going to be we have NS parallel chains. We initialize the chains by a given configuration. We do K steps, and later we take all the configurations at the end of the simulation and compute the expected value. Okay, it's a good approach if we manage to thermalize the chains, because if we don't thermalize, we could get whatever here. And to thermalize, we know that we need to do a number of steps that should be several times the mixing time of the algorithm in the model. Okay. Yes? Yeah, of the slowest observable. Okay, but of course we can only do it. But okay, I will comment this later. So we need to thermalize. We need that K is longer than the thermalization time. And something that is quite puzzling is that after decades of studies, I never find words that actually compute if they are thermalizing or not. Normally, the standard procedure is that it was introduced by Hilton with what actually who popularized the use thanks to this recipe. And the idea was, okay, we want to create samples that are similar to the data set. So we initialize our chain with the data set. We do some few steps, and we would have more or less a good approximation of this. Okay, this idea, it was a lot improved by a much better idea, which is, okay, since we are repeating this sampling many times during the learning, every time we have updated the parameters, we can reuse the last configuration we had in the previous sampling and use it as a starting point. So that since the parameters change very slowly, we would be more or less always in equilibrium. But again, with some few steps. And there are also algorithms using mean field, using the tap equations to improve the learning, but to improve the sampling, but it will be also some few steps. Okay, there have been also, but it has been also tried, and it can work well or not, to introduce temperature in the equation, so doing simulated annealing or doing parallel tempering to try to thermalize, but without computing the time. Okay, we have seen in our work that it was presented by Aurelian in a poster, and it has been accepted for NeurIPS just recently this week, that actually the RBMs operates in two distinct regimes depending on how we compute the gradient. If we use times that were shorter than the thermalization time, they are in what we call the non-equilibrium regime. And in this case, the machine that we have fitted, what it does, it has learned the dynamics that it was used to train it. So it's a machine that it's able to create new samples if you repeat exactly the same dynamics you used to train it. If on the contrary, we we sample times longer than the thermalization time, it learns a machine that, well, it learns the good model of the machine. That means we have a model that if we sample the equilibrium configurations, we get something that looks like the data set that it was in principle what we wanted to do. Okay, but how it does like the non-equilibrium regime. Okay, so as I said, it learns the dynamics. So if we want to create new samples, we would like that if we start from a random configuration, we start to sample and we get numbers. Okay, so we can repeat during the learning exactly the same procedure, not starting from the data set, but we start from random, we train it like this, and later during the sampling, we do the same procedure. What we see is that if we do this, okay, we have trained it with doing 10 steps, we get, after sampling 10 steps, we start to get numbers with that different between each other. And when we do much longer times, we start to get a thick version of the numbers that have a lot of ones. And okay, they look like numbers, but it doesn't seem to be okay. If we do it with using chains of 100 steps, we get the same thing, but in this case, the good numbers start to appear at 100 steps. But it's interesting to see that after that, everything seems to be very correlated and poor. That's clear that the equilibrium model that we have fitted with this model cannot be a good model for MNIS, for instance. Okay, if the machine learns the procedure to create repeating the same dynamics, this means that if we train the machine using contrastive divergence, which is, as I said, initializing the chains from the data set, it means that if now, during the sampling, I start from random and I start to sample, what I see is absolutely nothing. I don't create numbers ever, okay? But, okay, we could say, okay, let's repeat the same procedure it was used during the learning. So I can also initialize from the data set. But what do we find? If we initialize from the data set, basically we get the same numbers we had in the data set and nothing else. At a certain moment, at long times, they are going to even disappear. So we have a machine that does numbers, but does the numbers that we already gave it. So contrastive divergence is completely useless, I would say. And it's quite astonishing that a lot of people, especially in the physics world, are continue using it. I mean, it gets good values of the log likelihood, but as generative model, it's terrible. Okay, we could, I spoke about changing the initial conditions, but we can also change the dynamics. We can say, okay, we can train a machine using mean field steps, and later we do, okay, we have the machine which was trained. Even this one, I think it was done with 100 steps, so we did much longer trainings than unusual. And if we try to sample this using Monte Carlo dynamics, the hit-bad updates, we see that we don't get numbers. It looks more like numbers than in the previous case, but these are not numbers. But on the contrary, if I do the sampling also using mean field dynamics, we do find the numbers at the same number of steps that we have used during the learning, and from now on, it seems frozen. I mean, we rest there and nothing else. So the non-equilibrium learns the dynamics to learn it. Okay, we also tried to quantify a bit the idea that I was showing you before. So we introduced in the paper, we have a lot more in the poster, some others, not all. We introduced several observables that try to measure how good are the samples we are creating. In particular, for instance, we can compare the 2-point correlations between the original dataset and the dataset we are generating. Or here we can compute the power spectrum density with the Fourier transform. And what we see, okay, the different colors is how many updates we did in the machine, but for my speed right now, for my speed, it's not very important at that point. But what we see, which is interesting, is that we get a peak of very good quality at a certain moment at 10 steps of sampling. And if we go on the sampling, we get something that it's really worse. It looks worse than the data set. And it's interesting that if instead, okay, here I train the machine using 10 steps and I get the best quality at 10 steps, but if I use 100, I get the best quality on 100 steps, and so on. And what is quite interesting is that the quality of the samples that I get with the training of 10 steps is as good as the one that I train with a lot of steps. So using short chains, we can get samples that are quite good, but we have to be careful and use the sampling at the right time, because otherwise we get something that is very bad. Okay, what happens with the equilibrium regime? Okay, we can do the chains as long as to be able to thermalize in another time. And if we get this, we get models that are whose dynamics is a lot more simpler. I mean, we can compute here, for instance, the quality of the samples that we generate, and we see that, okay, we evolve. I mean, the more we train the machine, the better are the samples that we are able to create. But at a certain moment, we see that this equilibrates and remains constant. Okay, if we look at the samples that we are generating, we can see, okay, for a long time, we don't generate anything. But from a moment that we start to generate numbers, if we continue the sampling, we see that we start to generate other numbers. I mean, we have a model that it's able to generate numbers whose dynamics is a lot faster than the ones that I was discussing before. We don't get trapped there, and we have a good model for the data. So, as I said, we have these two regimes. The non-equilibrium that we learn the dynamics, that we think that it's actually a very good regime to generate data. If our goal is not to learn the model, is to generate good data, this is the best way to do it, because you don't need that long trainings, and you can get data which is very precise. I didn't enter here, but so often we get that data that it's better than if we did for the same number of training steps, we did equilibrium. So at a certain moment, equilibrium, it has to be well if we train well the model, but for data generation, it's good, but we have to remember that we need to train the data starting from a configuration that is reproducible. It can be noise, or it could be all white, not the numbers, but something that we reproduce all the time. Okay, this effect actually had been found in convolution and generative networks, where training is a lot harder than here, a lot longer, and they have also tried to do it in the Boltzmann machine. That is, we don't have any kind of latent variables after adword work, and they find it also. So it seems to be a characteristic of energy-based models. Okay, so What's the problem of the equilibrium model? If you don't use exactly the same procedure in training and in sampling, you are going to get a machine that seems completely unpredictable, because you can get samples that are very bad, but if you do it sorted, they are good. If you change the procedure, you can get nothing. So it's something that either you control it or it's completely unpredictable, and this explains the difficulties of training the RBMs. It creates models that have very complex dynamics, and they are extremely slow. In fact, we have seen that if you force the machine and you train it really out of equilibrium, you end up with a model that is clearly a spin glass, or it seems a spin glass. Okay, so we have, in the other hand, we have the equilibrium model, and as I said, in this model you learn a good model for the data. So this is the model that we should use. This is the regime that we should use if we want to do reproduce. We want to study the model that we train, because with this model, I don't know, it might be useful for interpret the data, it might not. We don't know. They are weird models. So these are the models for interpretability. One of the nice things is that if you train well the model in equilibrium, if you do the sampling, it's not that tricky. You can get good samples no matter what time you get. The problem is that, of course, you need to do large values of case. This is slow. And also, if you want to use it for generative purpose, you can face that maybe to generate new samples, you need extremely long sampling. So in practice, it can be impossible to do it. So for generating this one, for studying the model, the other one. Okay, so I was saying that we need to equilibrate, but the question is, how long do we need to do sampling to equilibrate? Okay, here we did it with MNIS, which I can tell you that it's an easy data set to learn. We can compute, for instance, the autocorrelation time of the magnetization. We tried several observables, but okay, this was the slower one. Okay, we can measure the magnetization correlation time for different, as we train the machine, and we can fit a characteristic time of this curve. And what we see is what I plot here in the black curve, is that the longer we train the machine, the slower it gets. So if I want to train the machine for a lot of updates, I need to do samplings that get longer and longer in time. Okay, in parallel, we also try to estimate the thermalization time, for instance, doing samplings starting from two very distinct configurations and seeing when we converge to the equilibrium, and we can see that this scales with the mixing time, but at higher values. But this is the thermalization starting from random, probably starting from the data set, or for a PTD, it wouldn't be that long, but at least we know that we have to be longer than the mixing time. And this is quite problematic, because for MNIS, we see that at least we need 50 steps to thermalize. And the literature normally uses of the order of 10. So almost all the work that has been done on this, they have been done in the non-equilibrium regime, not in the equilibrium regime. But later, it can be a lot more dramatic when we go to the sequence data. For instance, I can show you for the gene, the one that the data set that I was saying that we have for the genome. Okay, we can try to compute the autocorrelation functions that we get. Okay, until certain number of updates, we get basically one. The system decorrelates almost automatically. And from the point that it learns, okay, these are the first 2 points that we get something that it's out of our reach to know what time it is. We don't know what are the thermalization times. We know that are above 10 to the 5 steps. So we cannot thermalize like this. And we can try to understand what is going on. I come back to what I was saying with the phase diagram. After the learning, we should start to see a ferromagnetic phase. So we should start to see directions at which we start to have a positive magnetization. Okay, if I plot I project our data on the directions of the first eigenvector and the second eigenvector, I see that, okay, when I didn't learn, we just have a broad cluster, no problem. But from the moment I start to learn something, this cluster splits up in two. And if we go to more directions, we can even get more. If we continue the training, we got something monstrous in which we have so many clusters everywhere in all the directions. And we know what happens with this when you do Monte Carlo. We have metastabilities. So we are getting, if we do a simulation, we are going to get trapped in some of the clusters, and we would need a time which is extremely, extremely long to thermalize. So this cannot be solved with parallel tempering. Parallel tempering doesn't work for coexistent problems or for first-order transitions. We need something that forces the sampling to visit all the states. So what is happening, more or less what I was saying, okay, we can see we are facing something similar to try to study the equilibrium of the easy model at very low temperatures, okay, where we would have, okay, we have, in the easy model, we know that in the absence of magnetization, we could have, it's equally probable to have positive magnetization or negative magnetization. In general, I don't know if you have tried, but if you take the easy model, you put it at very low temperature, you're going to find by symmetry breaking one of the two possible solutions, but you never visit the other one, especially if you have a large system, because the probability of jumping from one state to the other one decreases exponentially, in particular with the inverse temperature and the size. Okay, so what can we do? In principle, I mean, we need to do equilibrium. We need to force the system to visit all the possible magnetization. Okay, this, as I said, it happened for the GEN dataset, but I said before that MNIST was easy. It's something that we can already see just doing the PCA, the principal value decomposition of the data we had. For instance, if we do it in MNIST and we project along the two first directions, we get something that doesn't have a very clear, well, it doesn't have clusters for sure, but if we do it with the GEN, we get something that it really clear clusters. Our data, it's organized, it's very structured, and if we do it, for instance, with proteins, we normally get something similar. So we have learning in equilibrium data sets that are clusterized. It's hard. It's going to be very hard, and I mean, we can try to do PCD with improves the things, but still you're going to face this problem. So we have been trying to approach this. So we went back to a simpler problem and saying, okay, I can generate, well, I can do clustering. Imagine I want to feed the machine with a data set of few clusters, and I would like that the machine is able to create points in every cluster, but with the right weight for each one. So we took a case that in which we know that we can get a model that is perfectly trained, which was done in a recent work also by Aurelian and Cyril, in the case in which we have clustering in high dimensions, but in which we have 5 clusters which are only separated along one of the spatial directions. In that case, they can solve the problem analytically and get a perfect model. So I saw here, if we have these data sets in high dimension, if we do the PCA, it does it very well. It finds the proper direction, and we get all these clusters. And okay, the first AN vector splits up the data in these 5 clusters. Okay, what happens? So we have this. These are the projections of the data along the proper direction. I call it the magnetization. What happens if we do Monte Carlo with this? We know that we have a model that has 5 states. If we do Monte Carlo, we just get trapped in one of the states, which, by the way, is not even the more probable one. Okay? So we have a clear problem of sampling. So as I said, we know that in general the solution when we have coexistence is to try to do bias sampling, to try to force the simulation to visit the magnetization in between so we can sample all the clusters. Okay, this we have solved it with the Tethered Monte Carlo approach, which I'm quite acquainted with because it was part of my PhD thesis. And the idea is we can see it just as a trick. Okay, we have the partition function. We can see that if we multiply our Gibbs probability, we multiply it by an exponential, very peaked around a given value of the magnetization. After we integrate it out for all the possible magnetizations, we get exactly the same thing. Okay? So we can use this to define a tethered potential, which would be all the terms that we have here. This trick allows us that we can see that if we want to compute a mean value in our model, this is equivalent to do the integral of the mean value obtained at fixed value of m hat multiplied by this potential. So what we can do is to do simulations at fixed value of m hat. So we fix that the magnetization should fluctuate around the value that we fix. So we don't have any kind of metastability in the simulations. So simulations are very fast. And once we have the mean values computed at fixed m, we can integrate it and recover the canonical probability. So until now, this could be just the umbrella sampling method, but one can see that this potential that we define it here, if we compute the derivative with respect to the constraint, we can see that we can compute it directly in a Monte Carlo simulation. It's just the difference between the value of the observable, the value of the constraint minus the value of the observable at the simulation. So in our simulation, we do several, here I don't know, I think it is 500 points. We can compute the gradient. If we have the gradient, we can integrate it numerically. And once we have the gradient, we can compute the probability in the tethered ensemble, and we get all the peaks. It's clear that here, if we have a large n, here we don't have this n is uncorrelated, but if we get a large n, this would be essentially like the Dirac delta. So this is essentially the probability of the magnetization. In fact, if we plot it with the data that we had before, the original data projected on the directions, we can see, okay, here I reverse the labeling. The red curve is the one that we obtained with the tethered. The blue one is the original data set projected. So we see that we can match the probability distribution function quite well. And if we have PDM, we can just generate samples according to the problem, just using inverse sampling and generating that. Okay, so coming back to the learning, what we have to do, okay, before we had many parallel samples to compute this. Here we are having parallel samples of different m hat. In practice, we also use some few samples in parallel to increase the statistics, but at the end, it's not very different from the point of view of number of simulations. Later, we can do the thermal average and the different clones. And, okay, we compute these observables in the m hat ensemble, and we integrate it out. So we can do it during the learning as well. And just I finish, we can also extend this approach quite easily to multiple directions, because in fact, when we do the PCA with these clusters, we see that it clusterizes also in other directions just by adding additional Gaussians centered on other ordered parameters. And in this case, instead of computing the derivative of the potential in the simulation, we compute the gradient that I saw here with arrows. And this here we did a learning using this ensemble. Here I showed you the tethered potential, and we see that, okay, we are managed to learn models that are able to catch these different isolated clusters of data and generate it accordingly. And okay, with this I finish. Okay, as I said, RBMs can be very puzzling when training, but now we know that the region of this puzzling behavior is related to the fact that you don't thermalize. So if you don't thermalize because you cannot, because it's too slow, okay, let's profit the non-equilibrium regime. You just mimic the sampling with the learning, and it's great. You create good samples. And you can do very good samples using short trainings. I couldn't show the GIF, but we can get very good phases, for instance, or very good numbers. And also with the clustering things, it can be sometimes a bit strange, but also it works. I mean, our sampling, Monte Carlo sampling, fails if we try to do it. It gets stuck in one of the states. But if you use the non-equilibrium regime, you manage to sample all the clusters at short times. If you get longer, you get trouble. And as I said, data sets that don't have a structure, they can be sampled easily. Only thing that you must know is that the longer you train, the slower it's going to become, and you can understand it that it's like decreasing the effective temperature. So it's as if you were considering the system as lower temperature. But if we have a structured cluster, we have to face that you have metastability between states, and you must find an algorithm that is able to break this metastability. Otherwise, you never will be able to thermalize, even if you use parallel tempering. And that's
Thank you very much, Beatriz. That was really interesting. And I'm sure there's a question. Let's start right here.
Thank you, Beatriz, for a very interesting talk. I have two questions. The first one relates to the first part of your work, where you describe the number of Monte Carlo steps required when going from a random initial configuration to a proper one, and how many steps are required, and the connection to sampling. So how does this extend to the PCD regime?
Okay,
where,
the PCD. Okay, yeah.
Because you don't relax from a random initial configuration.
We have studied. I mean, I didn't put it in the talk because PCD is more complicated to analyze. Because since PCD is the one that I said that you start always from the chain you had before. Okay, the parameters change really, really slowly, especially if you have done the training for a long time. So you can see the PCD sampling like a very long sampling because the parameters are changing so slowly. What we see, okay, with PCD, if you want to do equilibrium, it's clearly the right thing to do, because at least even when you do a small number of steps, you get something that at least is stable. You get samplings that are more or less stable. But they are not very good. I mean, if you compare the model you get with, for sure, it's much worse than the model if you had done equilibrium with, when you had done PCD with much longer values. Okay. And you get samples that are worse than if you did the non-equilibrium regime.
Okay.
So PCD helps you to get something that at least it's a good model for the data. It's worse model than if you did with longer case. For instance, with MNIST, the nice thing is that, okay, your thermalization time effectively is longer. So when you are doing PCD-10, you are really doing the random much longer, so you get more equilibrium. But we saw, for instance, if you do MNIST with PCD-100, more or less you do it, we did equilibrate it all the time.
Okay.
But PCD with 10, it's really too little. And if we go to the proteins, for instance, with PCD, we started to observe the non-equilibrium, non-monotonous equilibrium behavior. I mean, when you get times that really gets over even the effect of the parameters, you start to see it also. The problem is that with PCD, it's impossible to repeat the sampling accordingly because you don't know which is the configuration at the beginning. So you cannot profit the non-equilibrium regime.
Okay, thank you. My second question regards the bias sampling procedure you developed. So can you comment on how much time you need to calculate the histograms, and how does it, how does it work out with evolving models?
Okay, our best problem right now with this is that when it's with parallelization actually, because since we introduce a bias, one of the nice things of the restricted Boltzmann machine is that you can update at the same time all the variables, all the visible variables and all the hidden, because they don't interact with each other. When we introduce this term, we break this. So we need to do the sampling one by one. We can do in parallel all the M hat, but we get things, if we want to do 100 steps, we get something that gets 100 times slower. So by the moment, we are still trying to understand how many steps do we need to do. So right now, it's too slow. But we hope that we will be able to do it better.
Yeah, so I have one question. When you say, so if I understand correctly, you say that short training and short sampling generate good samples. Is it what you said?
Yes, if generate good samples at a very precise point.
Yes.
Otherwise, no.
But how far away are those generated samples from the data points?
It depends. I mean, they are, for sure, we saw that they are as good as if we do the equilibrium model at the same number of steps.
Good, but I mean, in terms of diversity of entropy?
Yeah, in terms of entropy, I mean, one of the quality measures that we were doing, for instance, it was the entropy.
Okay.
I mean, we don't distinguish, it's not better, the equilibrium ones than the ones of non-equilibrium. The point is that later, to get better samples that look, I mean, we found, at least with MNIST, we didn't manage, because we were looking that we had diversity, we had all the numbers represented in the right amount, not having a lot of ones or having a lot of zeros. But we have a variable that we are not controlling if the numbers are thick or very narrow. And this, I mean, we only solve it, for instance, or adding an extra layer, this we did it, or using a lot data set which are much larger. But it was not related to the equilibrium or non-equilibrium regime. I mean, with the model we were using, you get something that is really comparable. And in fact, in the work that we discovered during the referee process, these works, they managed to get images with these convolutional generative networks that are really comparable to the ones that are done by the GAN. But they have to exploit this. They have to do it, exploit the non-equilibrium regime.
Okay, I think we're going to thank Pierre again for the question.